been at Uber for about 4 years. And there I have co-founded a couple of teams, including our natural language and conversational AI efforts, our anomaly detection team, and forecasting platform teams. In addition to that, I lead a couple of other data science teams as outlined on the slides. Before joining Uber, I was a postdoc at Caltech working on approximate quantum dynamics in order to study complex biological systems such as enzymatic reactions. I would like to give a huge shout out to the cross-functional and cross-organizational teams that are deeply involved in building our natural language and conversational AI efforts at Uber. In particular, I would like to thank the individuals shown on the right-hand side of the slide who are the active contributors to the work that I'm going to present today. So what are the key takeaways from today's talk? Well, firstly, at Uber, we have dozens of natural language and conversational AI use cases. And if you're interested in working in this domain, please feel free to come and see me over lunch. We're very actively hiring in this space. Secondly, we not only have use cases, but we're also already actively employing and using natural language and conversational AI in order to improve the user experience. And so today I will go in detail into 2 of these use cases. On the left-hand side, you can see the so-called customer obsession ticket assistant. This is where we use natural language processing in combination with machine learning in order to empower our customer service representatives and provide an enhanced customer experience to our end consumers. And then on the right-hand side, you can see the so-called one-click chat. This is a recent feature that we launched, which allows driver partners to respond to incoming messages from riders in the app at a push of a button. In the final part of my talk, I will be addressing some of the core components that are recurring within conversational AI systems. And in combination with the large number of use cases that we have at Uber, this really lends itself very well to platformization. So let's get started with the first use case. As I mentioned, this is CODA, the Customer Obsession Ticket Assistant. And as mentioned on the previous slide, we use here a combination of natural language processing and machine learning technologies in order to provide an enhanced customer support experience. Now, whilst this is a specific use case and potentially specific to Uber, there are some general key learnings we can take away from this use case, and these are threefold. Firstly, deep learning methodologies have been found to be extremely useful in this space and often outperform the traditional employed methodologies. In the case of CODA, we'll see that deep learning natural language methodologies outperform the traditional ones by over 20%. Now, that being said, if your company has not yet invested in deep learning infrastructures, the traditional methodologies still provide a very solid first starting point. And I'm going to address both the traditional methodologies we have investigated and deployed, as well as those in the deep learning space in the following slides. And then finally, as everyone knows in this room, model accuracy is not everything. And also here, with this particular use case, we had to make a trade-off between model accuracy as well as speed of computational inference, as well as training. So why would we want to invest in such a customer service representative assistant? There are 2 areas here. One is that we have a very large volume of tickets. We get millions of support tickets every week from our riders, drivers, eaters, couriers, freighters, etc. So pure scale is one aspect. But then there's also the complexity. We have thousands of different issue types, and this complexity only increases as we add new lines of businesses, for example, scooters and bikes. So let's delve a little bit more deeply into what such a customer service flow looks like. First, the user who has a question or encounters an issue would be navigating within the app or in our web application to the help page and then submits a support ticket. This is often accompanied by a couple of sentences around the description of what the issue is. Now then, the customer service representative receives this incoming ticket and needs to do 3 major things. Firstly, they need to figure out what the actual issue type is, as in how this issue that the customer has described maps into the so-called contact type tree, which is the collection of all the issue types that we have. Then, secondly, they want to understand whether an action might have to be taken. So, for example, an issue type might be a cancellation, and an action might be an appeasement that the customer service representative can give. And then finally, we want to close this out by responding to the user who has written in. And here, the customer service representative can pull from thousands of different reply templates and use these as a starting point for their response. Now, this all seems very straightforward, but if we go a level deeper and actually look what the customer service representative needs to do here, then we can see this is a quite complex and non-straightforward task. And this goes to a little bit what I alluded to earlier in terms of the complexity. We have thousands of different contact types that are arranged in a contact type tree, which can be quite deep, between 3 and 6 layers. We have several actions that the customer representative needs to choose from. And then finally, there are thousands of potential reply templates that they can draw from. So based on this, we saw the opportunity of using machine learning methodologies in order to empower our customer service representatives to provide high-quality customer support at scale and to dynamically adjust to incoming volumes and ticket types. So CODA basically, what does it do? It takes the incoming support ticket and then understands what the intent of the customer is. It uses a lot of the meta information as well, and then provides suggested contact types, actions, as well as the 3 most relevant reply templates to the customer support agent, and then they can choose to use these or not. So let's delve a little bit more deeply into the models that we were using for this customer service representative. I will be starting off outlining the traditional approaches that we used, and then subsequently we're going to delve into the deep learning approaches. So for the first iteration of CODA, we built a traditional NLP pipeline in combination with a random forest. We used 4 different types of feature types here, ranging from the user information to trip information, metadata around the tickets, as well as the ticket message itself. Now, using these features can be very advantageous because it reduces greatly the potential reply and contact type space. To give you a concrete example, if we know that a ticket is coming from a driver partner, we can immediately exclude any issue types that would be submitted from writers, for example. Now, unsurprisingly, the incoming message from the user itself is being found to be the most important feature within this model. And so in this case, we used the traditional NLP pipeline, which consisted of pre-processing such as tokenization or stop word removal to yield a bag of words. And then we utilized topic modeling on top of this bag of words in order to extract the intent of the customer. Now, here we use 2 different approaches. We use TF-IDF for low-level NLP feature extraction and latent semantic analysis for high-level feature extraction. Now, we then take all of these features and pass them through a multi-class classification algorithm, in this case, a random forest, to yield the top 3 contact types as well as top 3 reply templates. Phrasing this as a multi-class classification problem seemed the first natural thing to do, but what we realized is the model accuracy was not quite where we wanted it to be. So therefore, we pivoted the approach to a binary classification with point-wise ranking methodology. And we also introduced class prototypes for each specific reply template, as well as contact type, a specimen, so to say, that we got from historic data. We then use the output and the score from the binary classification for the ranking, again, to obtain the top 3 contact types and top 3 reply templates. Now, this approach was 25% more accurate than the multi-class classification approach, and in addition, also provided much faster training times. So given this success, we then went ahead, productionized this model, and ran some A/B tests. And we were very excited to see an 8.8% reduction in the average handle time, which directly means that the customer can get their tickets resolved much faster. And very, very importantly, we didn't see any reduction in the customer satisfaction score by deploying this model. Now, this model is live for multiple different languages, including English, Spanish, and Portuguese, and covers over 90% of our ticket volume. Now, as I mentioned earlier, deep learning methodologies have been very dominant in the natural language and conversational AI space. And so we want to also test whether deep learning approaches could be beneficial to this customer obsession ticket assistant. To this end, we evaluated 6 different text encoding models. These differ by 2 major things. The first thing, whether we use word or character-based approaches. Now, character-based approaches can be very good if you have misspellings or out-of-vocabulary words. We also had both convolutional neural networks or recurrent neural networks as well across these 6 approaches. And as you can see on the far right, we have also hybrids between these 2 as well. Now, recurrent neural networks obviously can very nicely capture the sequential nature of the incoming text. On the other hand, CNNs tend to be much faster. So let's look at the outcome of comparing these 6 different models for our particular use case. As you can see, the hybrid CNN-RNN method based on characters was the one with highest test accuracy. Now, as you can also see, it was by far the most expensive. So this basically then meant that when we went to productionize this model, we went with the second best model in terms of test accuracy, the word CNN option. Now, whilst we still went with the second best, this still gave us a huge lift over our traditional methods. We saw over 20% improvement over the random forest method that I described earlier. We then improved the model further to encapsulate some of the hierarchy from the context type tree. As I mentioned in the introduction, all of these issue types are assembled in a tree. And so we wanted to make sure that we could capture the path from the root node down all the way to the leaf node as part of our model, instead of just predicting the context type independently. And this obviously would also give us gains in terms of the model accuracy. So the way that we accomplished this was to use a recurrent decoder, where we used as input the top node of the tree, and then basically fed it in to yield the child node as the output, which we then fed in again, et cetera, until we ended up at the leaf node. So as I mentioned, the advantage here is to get higher model accuracy, but much, much more importantly, it provided a much better user experience to our customer support representatives if the model was wrong. Because in this case, if the model is wrong, we're still typically ending up in a similar space in terms of the context type tree of where the agent wants to be, and they're only 1 or 2 clicks away from the actual solution, versus if we do not employ this, we can end up in a very distant space on the context type tree, and it's very hard for the customer service representative to return. So let's, in summary, step back and look at the final architecture that is shown on this slide. We already went in depth about how we encoded the text features via convolutional layers. As you saw from Coda V1, there were a lot of other features that we wanted to incorporate in this model that gave a lot of signal. These were categorical features, which we encoded using embedding layers, numerical features that we encoded using batch normalization layers, and then, of course, we also included binary features, for example, is the trip completed or not. And then we concatenated all of these together and fed them through fully connected layers with dropout. In order to obtain the context type, we utilized the recurrent decoder that I showed you on the previous slide. And then in order to get the reply, we used a softmax classification. And importantly here, we also inputted the type as an input feature as well. And that, of course, also helps us, again, to to increase the accuracy of the model, because once you know what the issue type is, for example, a cancellation, you can immediately reduce your contact type space in terms of the reply accordingly, and know that you only need to focus on reply templates that are related to cancellations. Now, obviously, when we train, we use the ground truth type data in order to inform the reply. And when it comes to the testing, we use the predicted contact type in order to predict the reply. So this concludes the overview of the Customer Obsession Ticket Assistant. And I will be pivoting now and talking about the second use case, our one-click chat OCC use case. As mentioned earlier, here we're utilizing natural language and conversational AI in order to assist driver partners in quickly replying to incoming messages from the riders. And here we will see two things. One is that semantic understanding is extremely important. And the second thing is we will be showing how we can use a very small set of labeled examples in order to be very effective in this intent discovery. So let's reframe this problem in the lens of natural language. So as previously seen in the CODA example, the first step is to take an incoming message and to map it into an intent. So for example, the writer might be saying, "Where are you right now?" And then we want to map this to the topic of "Where are you?" Now, contrary to the previous example, we didn't know what the potential rider and driver topics were that people were talking about. So as part of this project, we also had to first do intent discovery as well. Once you actually have the intent, it's very straightforward to go to a reply. We have some preset replies for every single intent that we discover, and then we basically surface this in the driver app for the driver partner to select. So there are quite a lot of challenges associated with this project. The first one is that the message is very short. It often contains typos and abbreviations, as you can see here from real data on the left-hand side. And autocomplete is often not our friend. As you can see at the bottom, we have here a sentence, "I'm Washington for you," which clearly should be saying, "I'm waiting for you." So whatever methodology we use, it needs to be able to disentangle this as well. Some of the other challenges that we might be facing on this front are that we have perhaps different words, but with very similar meaning, as shown in the middle column. And then on the very right-hand side, you might have a lot of similarities in the words between these two sentences, but they actually have very different meaning in the context that we're talking about here. So as seen in the previous slide, we need to be able to capture the semantic understanding extremely well. And in order to do this, we use the unsupervised learning methodology doc2vec. This is an expansion of word2vec. Word2vec basically allows you to come up with word embeddings. Doc2vec allows you to come up with things like sentence or paragraph document embeddings when you employ it. So we basically used millions of English Uber chat data, and they basically ran it through the doc2vec model. Now let me show you what this looks like. Here we see a Disney plot of some of the sentence embeddings that we got. As you can see, we get some really, really nice clusters here of various different topics that riders and drivers are conversing about that our data scientists then labeled. So this brings me to the next challenge, which is obviously that these clusters come out unlabeled in nature. And so we basically hand-labeled a couple of thousand examples to then basically determine what these clusters actually mean and what the topics of conversation are. The rest is pretty straightforward. We calculate centroids of each of these intent clusters, and then this concludes the training phase. Whenever we have an incoming message, then at runtime, we calculate the distance between this message and the intent cluster centroid, and then we assign it to the nearest cluster. So with this, we basically conclude the intent detection and discovery phase of this project. And as I mentioned in the introduction, the reply retrieval is merely a lookup of potential responses that have been predetermined. So now let's go back to the original example, the real-world example that I showed you. I'm Washington for you, and actually when we utilize this approach that I just showed you in the previous slides, it correctly identifies that Washington should be waiting. And so there's a big advantage that we have from actually using our data and building the sentence embeddings ourselves, as it can pick up the context within our ecosystem. So next, I want to give you a glimpse of what the future looks like of one-click chat. We obviously want to not only provide text modalities, but also voice.
New message from Yizzy. I'm waiting by the Starbucks. Do you want me to respond?
Tell Yizzy I'll be right there.
Okay, sure. Ready to send it?
Send it.
Great. Message sent.
So these new features that we're building will allow driver partners to also provide answers to the riders using their voice, which is very exciting. And in my final part, I want to tell you a little bit about the building blocks that many conversational AI systems have in common. And as I mentioned in the introduction, the combination of having a large number of use cases at Uber for natural language and conversational AI with the fact that a lot of this is abstractable really lends itself well to platformization. So in the previous examples, we have seen that we really need to understand the intent, so basically the topic of conversation of the end user. And so this is typically handled by a semantic parser on this front. Now, so far, we have only seen single-turn conversations, so one incoming message, one response. You would probably want to evolve this to a multi-turn conversation with a back and forth. And here, the dialogue manager comes into play, who, for example, tracks the state of the conversation. And then finally, we want to move from a semantic representation, which is not human understandable, back into something that can be consumed by a human being. And here, the language generator comes into play. We are actively building such a natural language conversational AI platform at Uber, and we're actually using some of the latest cutting-edge technologies. And not only that, we're actively working with our counterparts in our AI labs, our research division, to push the envelope on these methodologies as well. And so if you want to learn more, whether it's about the applications that I've shown you today or about the new developments that we're doing in this space, we have several blog posts on our UberEng blog. We have a recent paper at KDD, and we have 2 submissions for NIPS, where we're also going to talk about some of the multi-turn conversational AI endeavors that we have been starting. And with this, I would like to thank you very much for your attention. And if you have any questions, I'm happy to discuss them over lunch. Thank you very much.